In this video, we're going to start looking at sequences and series. A sequence is a set of ordered terms that are obtained by some rule. That rule might be as simple as add 1 each time or multiply by 4 each time. We could have a different sequence. We might have 3n minus 1 or 4n plus 6. A series is the summation of a sequence. Let's write down the first 5 terms of a sequence. 1, 4, 9, 16 and 25. We should recognise these now as square numbers: 1 squared, 2 squared, 3 squared, 4 squared and 5 squared. So the rule is to square the number. We can say the general term of a sequence is a sub n, and in this particular case we've got n squared for n from 1 to 5. Let's look at this notation here. I said sub n. Sub just means subscript, so we got a small n. So if we wanted the 100th term, a sub 100 is equal to 100 squared. I've used a in the module or the unit. You might also see u being used. So u sub n is n squared. This is a sequence. We could write it as a series as 1 plus 4 plus 9 plus 16 plus 25, and we could go ahead and sum the first 5 terms. I can do this manually, and that will now give me 55. In later videos we'll look at more challenging summations and look at some of the formulae that we can use for that. What we're going to do in this video is work through some basic sequences and then move on to our first topic of recurrence relations. So let's go ahead and generate some terms in a sequence. I'm going to say now that u sub n is equal to 2n plus 1, and what we're going to do is now find the first 4 terms. What I suggest doing for the first few attempts is to keep on top of your bookwork, as I call it, and write down now a list of values. It might seem tedious. Initially it really will seem very tedious, but it means that you keep your work in order, and then when we come on to some more challenging examples, you've got a track of what you've been doing. So if we now take n to be 1, that gives me u1 or u sub 1, and that's 2 lots of 1 plus 1. So we can see that u sub 1 will give us 3. If n is equal to 2, we will get now the second term in the sequence. That will be 2 lots of 2 plus 1, which is 5. If we take now n to be equal to 3, u sub 3 will be 2 lots of 3 plus 1, which will give us 7. n is equal to 4, we would have u sub 4, and that's going to be 2 lots of 4 plus 1, which is 9. So if you're asked to write down the first 4 terms of this sequence in an exam, you would be expected just to write down 3, 5, 7 and 9. You might now recognise this as an nth term problem that you've seen in the past. So this is our nth term formula. We would say that this is an arithmetic sequence. In this unit we spend a lot of time looking at arithmetic sequences and series. An arithmetic sequence has a common difference. So 3, 5, 7 and 9, it's going up by 2 each time, and that's that value there. So as stated earlier, quite tedious to write all of this out, but it gets you in good habits in terms of generating terms in a sequence. So for example, if we had a constant involved as well, writing this out will allow us, for example, to sum a series given a range of different expressions that we've generated. Let's do another one. Let's do a sub n. Let's do a sub n, and we will say that this will be minus 2 to the power of n multiplied by n. And what I'll do, I'll generate now the first 4 terms of this particular sequence. So let's take n to be equal to 1. So subbing it in, we've got a1, and that will be minus 2 to the power of 1 multiplied by 1. That's minus 2 times by 1 is going to give us minus 2. If we take now n to be equal to 2, we have a2 or a sub 2. That will be minus 2, which we're going to square, and multiply by 2. Minus 2, if we square it, will give me positive 4. Multiplied by 2, we get 8. So the first term in the sequence is minus 2. The second term is 8. If we take now n to be equal to 3, a sub 3, we're going to get minus 2. We're going to cube that and multiply it by 3. That'll give me minus 8, minus 24. If we take now n to be equal to 4, we have the fourth term, a sub 4, and that's going to be minus 2 to the power of 4 multiplied by 4. That'll give me positive 16. 16 times by 4 is 64. So we've gone ahead and generated terms in these sequences. With this particular form, these are given as an nth term formula. So I can jump to any term in these particular sequences. So if I wanted for 100th term, u sub 100 or u100 is 2 lots of 100 plus 1, which is 201. If I wanted for 40th term, a sub 40 is minus 2 to the power 40 multiplied by 40. So these now give us nth terms or explicit formulae for these particular sequences. What we're now going to look at are recurrence relations. A recurrence relation is a relationship that links terms in a sequence. So what will be given is a recurrence relation will be given an initial condition and then we will find subsequent terms. Many sequences can be written both as these nth terms and recurrence relations. Some can just be written as recurrence relations. So let's go ahead and look at an example of one. What we'll do, let's just write one out. Let's go for u, and we'll write this down. U sub n plus 1 is equal to 3u sub n, and then we'll add 1 to this. We'll be given this initial condition, and in this case, let's just say u sub 1 is going to be equal to 2. What we'll be asked to do now is find u2, u3, and u4. If you wanted to read this in your head, the next one is 3 lots of the last one plus 1. And again, you might find that generating these terms quite tedious writing them all out. So let's now take n to be equal to 1. If n is equal to 1, if we just put in 1 here, we're going to have u2 will be equal to 3 lots of u1 plus 1. So we're going to have 3 lots of 2, 3 lots of the last one plus 1, and that's going to give me 7. If we take now n to be equal to 2, we will have u3, we've got 2 plus 1, and that will give us now 3 lots of u2 plus 1, or 3 lots of the one before, so that's going to be 3 lots of u2. We know that u2 is 7, plus 1, that's going to give us now 22. If we take now the next one, this is going to be when n is equal to 3, we're going to have u4. So we've got u1, u2, u3 and u4, and all we're going to do is 3 lots of u3 plus 1, 3 lots of 22 plus 1, and that's going to give us a total of 67. So I've generated now these 3 terms given the first one, or the initial condition that u sub 1 is 2. And again, you might say, well, that's fairly tedious because all I'm doing is going to multiply the last one by 3 and then add 1. Again, when a constant comes in, for example, if we've got a P and a Q or an A and a B in there, keeping on top of your work can be really quite helpful. But again, look at the mark allocation in an exam and see what you have to do in terms of working. Right, let's have a look at another one. Let's generate some more terms. So this is a recurrence relation. So what we're doing now is basing it on the previous term. So in this particular one now, if you wanted to jump to a term, you wouldn't. You would simply build it up from here. Now this time I've put u1. Don't be alarmed if you see u0 or a0. Generally speaking, in this particular module, we start with u1, but don't get concerned if you see u0 or a0. Okay, let's look at another one. Let's say we've got now, let's go for a sub n is equal to, let's go for a sub n minus 1 squared, and then we will minus 2. Let's have now an initial condition. Let's say that a1 is going to be equal to 3. And what we want to do is just generate now, let's find a2 and a3. So this scenario now, we've got a sub n is now the quantity a sub n minus 1 squared minus 2. And we've been given that the first term is 3. So if we now take n to be equal to 2, we're going to have a2, and that's going to be now a1 squared minus 2. So we can see that I'm going to take this number right here, so that's going to be 3 squared minus 2, so that's going to be 7. So we can see now that a2 is 7. If we now take n to be equal to 3, we've got a3, and that's going to be a2 squared minus 2. So we're going to have now a2, which is the term we just generated here, 7 squared minus 2, so we're going to end up now with 47. So that now gives us those terms. And as you can see, if I wanted to generate the next one, that's going to be a bit of a nightmare. But all we're doing is looking at building these up. We're taking the last term and then we're applying a term-to-term rule. And that's the idea of a recurrence relation. What we have is now this term-to-term rule, and we go ahead and apply it. As stated earlier, some sequences, for example the nth term ones that we've been looking at before, the 2n plus 1s or the 3n minus 5, can be written now as an nth term and a recurrence relation. So let's just look at an example of that. So let's say we've got u sub n is equal to 2n plus 1, and we just generated terms. We know that the first one, when n is going to be equal to 1, we're going to have 3, then we're going to have 5, then we're going to have 7, we're going to have 9. We could write this as a recurrence relation. We could say that u sub n plus 1 is going to be equal to u sub n plus 2, and we would state the initial condition that u sub 1 is equal to 3. So this is what we would have. These two things now give us the same thing. If you just look at the different forms, so this is our nth term, or our explicit form, and this now is the recurrence relation. As you can see, if I wanted now the 100th term, it would be easier to sub it into here than generate term after term. But as stated before, we can't always express particular sequences as nth terms, so we rely on a recurrence relation. Okay, let's look at a slightly more challenging example. Let's say we've got now u sub n plus 1, so we'll write down u sub n plus 1 is equal to p lots of u sub n plus q. And we'll be told the following. We'll be told now, let's say that the first 5 terms, let's write down first 5 terms, 2, 5, we've got 17, we've got 65, and we're asked to find now the constants. Let's go ahead and do this. So we've got the constants p and q to find. So what we've got then is this recurrence relation. So the next one is p lots of the last one plus q, where p and q are constants, and it generates now, let's just write these down, we'll put 4 terms in this particular sequence. So what we can see from here, if we just wrote this out, u sub 1 is 2, we've got u sub 2 is going to be equal to 5, we got u sub 3 is 17, and we got u sub 4 is 65. So what we can do is consider now different terms in this sequence. If we think now when n is equal to 1, what we're going to have here is u sub 2 will be p lots of u sub 1 plus q. So all I've done is taken n to be equal to 1. Now, if we look here, we've got u sub 2. Well, that's 5. We can see the second term is 5. So I can write 5 will be equal to p lots of u sub 1. Well, u sub 1 is going to give us 2. And then we're going to have plus q. So if we look at this now, we can write this as 2p plus q is equal to 5. So 2p plus q is equal to 5. And I'll just call this one equation 1. Okay, now if we look when n is equal to 2, what we've got then, subbing this in, we're going to have u3, so u sub 3 will be equal to p lots of u sub 2. In fact, let's just take the brackets out, don't need the brackets here. We've got p lots of u sub 2, so just clear those off. And then we're going to add to that q, so p u sub 2 plus q. So u sub 3 is 17, so we can put 17 is going to be p lots of u sub 2. Well, we know that u sub 2 is going to be 5, so we can put 5 in there, and then we're going to have plus q. So I could write this now as 5p plus q is going to be equal to 17, and I'll call that one equation 2. What we've now formed are simultaneous equations involving p and q. So all we need to do is go ahead and solve. So by writing out these little tables or little values, I've just kept on top of my work. So let's go ahead and do that. Let's just write these out. So we've got 2p plus q is equal to 5, and we've got 5p plus q is equal to 17. So if I just subtract downwards, what we're going to have then is minus 3p plus 0 will be equal now to minus 12. So we can see that p is going to be equal to 4, and then all we need to do is sub that in to find q. So if we put this into equation 1, we've got 2 lots of 4, plus now q is going to be equal to 5. So what have we got? Q is going to be equal to now minus 3. And again, you can go ahead and check those values, but they look pretty good. So that's a recurrence relation. We've got now a term-to-term rule, and all I've done is subbed in the values. I could have used other ones here, but I've gone for these. Just looking ahead, we've got the values, we write them down, and we can simply set up simultaneous equations to find these constants p and q. And I think just writing this down nice and neat does allow you to work that slightly easier. Okay, let's move on and look at something that's quite interesting. What I'm going to do now is write the following. Let's go for u sub n is equal to u sub n minus 1 plus now u sub n minus 2. And what we'll have now is u0 is going to be equal to 0, and we'll have u1 is going to be equal to 1. So sometimes we have u0 or a0 as stated. What we're going to do is start looking at generating terms. So we got the first two terms, u0 and u1. Let's go ahead now and generate some more. So what I want to do now is let's find a few more. Let's find u2, let's find u3, let's go for u4, let's write down u4. We might do a few more. Let's go for u5 and then write those down. So what we're going to do is start now with n is equal to 2. So if n is equal to 2, we're going to have now the following. We will have u2 will be equal to u1 plus u0. Let's just make that's not subscript, that's needs to be u there, doesn't it? So let's put u0. So u0. So what we can say then is u2 is going to be equal to u1, and that's going to be the 1 plus the 0. So we can see that that's going to be equal to 1. So let's put this just here. Okay, let's now look when n is equal to 3. What we're going to have is u3 will be equal to u2 plus u1. So we know u2, that's going to be this one, and we know u1. So what we're going to get then is 1 plus 1. And that's going to give us now let's put this on, what's that total? That's going to give us 2. So let's put 2 just here. As you can see, you can kind of do this in your head a little. u4, let's let n be equal to 4. So what we're going to have, u4 is going to be equal to u3, and then we're going to have plus u2. So what we're going to end up then with is u3, which is 2. So we're going to have 2 plus 1. So we're going to end up now with 3. So let's put 3 in here. Now, clearly you can see what's happening. When n is equal to 5, what we're going to have is u5, u sub 5, which is going to be u sub 4 plus u sub 3. So that's going to now give us 5. The next one we're going to get 8, then we're going to get 13, then we're going to get 21, then we're going to get 34, then we're going to get now 55, and then we're going to get 89. You might recognise this now as a famous sequence. This is the Fibonacci sequence. So what we can see is that having a recurrence relation, and the Fibonacci sequence is f sub n is equal to f sub n minus 1 plus f sub n minus 2. So it's simply saying that the next one is the two previous ones added together, and this is what we've got, and this is a recurrence relation. Now there is an nth term explicit form for the Fibonacci sequence, but that's certainly beyond the scope of this particular course. But as we can see now, we can generate these famous sequences by using a recurrence relation, and we hopefully know that Fibonacci sequences is simply the two before it added together, and that's an example of this. So kind of putting this into context, is often students see this as very kind of this thing of it's way out there and it's kind of a bit useless, but hopefully this is giving you a bit of an idea. And really this is tedious when all we're doing is simply going, well, it's the last two previous ones added together. But this now is the recurrence relation for the Fibonacci sequence. F sub n is f sub n minus 1 plus f sub n minus 2. Okay, let's look at another question. Let's look at the following. Let's say we want now u sub 1, u sub 2 and u sub 3. We're told now u sub 1 is going to be equal to 4, and we're told u sub n plus 1 is going to be equal to p lots of u sub n plus 2. And what we'll be asked to do now is find u sub 2. So with this one, you often are asked to write this down. Straight off in an exam, you'll generally be given 1 mark. So if we think about now u sub 2, all we're going to do now is the following. If we consider this is when n is equal to 1. So u sub 2 is going to be p, then we're going to have u sub 1. So all I've done is taken n to be 1, which gives me u sub 2. So that's going to be p, then we can have 4 plus 2. So we can say that u sub 2 is going to be equal to 6p. If we wanted now, we could generate the third term. What I'm going to do is switch this around a little and say the following. We're going to be given a sum, and I'm going to introduce this shortly. We're going to have the sum from r equals 1 to 3 of u sub r, and we're going to be told that that's equal to 2. And what we want to do now at this stage is find the possible values of p. So let's just look at this notation. I've introduced this sigma notation. Sigma is the Greek to sum. What this is telling me now is if I sum u1, u2 and u3, I'm going to end up with 2. So what we've already got just here, we've got u1 and that's going to be equal to 4. We've got u2 which is 6p. Now let's find an expression in terms of p for u3. So if we look at this right here, if I sub in n is 2, u3 is going to be p lots of u2 plus 2. So what we're going to have then is the following. We're going to have p lots of now u2 which is going to be 6p plus 2. This now is just equivalent to saying now, so we can write therefore u1 plus u2 plus u3. It's telling me to take r as 1, 2 and 3. So we start at the bottom number and go to the top. So if this was 5, we would take it up now to u sub 5. And we're told that this is going to be equal to 2, and what we want to do is find the possible values of p. So let's go ahead and do that. So what we've got then is 4 plus 6p plus, and all I'm going to do is just expand this. We've got now 6p squared plus 2p, and that is going to be equal to 2. So with our sigma notation, this is now saying sum all of the values from r is equal to 1 to 3, and that will give us the value of 2. So here are our terms. We've generated the first 3 terms. If we wanted to generate now the 4th term, if we now considered when n is equal to 3, let's just do that, we don't need it. If n is equal to 3, we would have u4, and that would be p lots of u3 plus 2. So all we would do is write u4 is going to be p lots, and then we would sub this in right here, which is going to give me 6p squared plus 2p plus 2, and then that would give us an expression. Fortunately, we don't have to include that, as it's going to make our algebra a little messy. So let's tidy this up into a quadratic equation in terms of p. 6p squared plus 8p, and then we're going to have plus 2 is equal to 0. We can divide through by, what can we divide through by? 2. 3p squared plus 4p plus 1 is equal to 0, and then we can factor. So we can have 3p plus 1, and then we're going to have p plus 1 is equal to 0. So we can say that p would be equal to minus 1/3, or we could say p would be equal to minus 1. So we've looked at a couple of things right there. We've looked at now generating terms in a sequence given now this particular recurrence relation. So the recurrence relation is u sub n plus 1 is p lots of u sub n plus 2. We're given the initial condition that the first term, u sub 1, is 4. And then we can go ahead and generate terms. We'd be asked to write this down. You'd be given 1 mark in an exam, and then you would be given far more if we were given some statement like this. So for example, now if it said, let's write something down, let's say now the sum from r equals 1 to 4 of u sub r is equal to 16, what we would have to now do is add this one in to this and then go ahead and solve this particular equation, which is going to be a cubic equation, and hopefully some terms will drop out and it'd be quite easy to solve. But that's just taking us on to the next level. In a future video, we are going to deal with sigma notation. This is just a brief introduction in the framework of recurrence relations. So whilst I'm not dwelling too much on it, it's just giving you some understanding that this just means to add up. Sigma, Greek notation for summing. Okay, let's just finish with a practical application of a recurrence relation. So let's say I start a fitness regime, and what I'm going to do, let's just make one up, a fitness regime, and what I've got near my house is a running track. So let's see if I can draw a running track. Let's see how good my running track's going to be. Okay, there it is. So what we've got then is a running track, and in week 1, so let's write this down, in week 1 I'm going to do 1 lap. So week 1 I'm going to do just run round. So if I start here, I'm just going to go around once. Each week I'm going to do twice what I did the last week and then add half a lap. So each week after, and let's just write this down, so each week after, and let's just make something up as we go. Each week after, I'm going to do twice as much, so twice as much plus now 1/2 a lap. So plus half a lap. So what we want to do is write a recurrence relation for this. Then I want to find out how many laps, so let's write some questions. How many laps have I done? How many laps do I do in week 4? So do I do in week 4? That'll be our first question. And how many laps have I completed in total? So how many laps in total have I done in 5 weeks? In total, in 5 weeks. So let's just go through this, as it might not be too clear. So I've started a fitness regime. In the first week, I'm going to run once round the lap. Every week after, I'm going to do twice what I did before, plus another half lap. So let's go ahead and write this out. What I can write now is u sub n, so u sub n plus 1 will be equal to 2 lots of u sub n plus 1/2. So this is saying the next week I'm going to run twice what I did the week before plus half a lap. And we're given the initial condition that in the first week, u sub 1, the first term in the sequence now, is going to be 1. So let's go ahead and work out how far I run in the subsequent weeks. So what we've got then is u1, and that's going to be 1. If we now consider u2, I'm just going to do this manually. So we're going to have 2 lots of 1 plus half, which is going to give me 2.5, which I'm going to write as 5/2. Then I'm going to have u3, and I'm going to have 2 lots of the one before plus a half. So that's going to give me 5.5, and that'll be now 11/2. So all I'm doing is simply putting 2 lots of the last one and adding a half. If we look at the next one, I'm going to have 2 lots of the one before, so it's going to be 2 lots of this one, and then we're going to add 1/2. So that's going to give me 11.5. We could write 11.5 as 23/2. If I now look at the 5th term, I'm going to have 2 lots of this, and then I'm going to add a half. So that's going to give me 23.5, and we could write that as 47/2. So I've quickly generated these terms. If you wanted to do it more formally, if you now let n be equal to 1, what we'd have is u sub 2 is equal to 2 lots of u sub 1 plus 1/2. So we'd have now u sub 2 is going to be 2 lots of 1 plus 1/2. So we could see now that u sub 2 is going to be equal to 2.5, which is 5/2. And then, of course, you can keep going with this. N is equal to 2. We would have now u sub 3 is 2 lots of u sub 2 plus 1/2. And we can see we're just generating these. So u sub 3 is going to be 2 lots of u sub 2, which is 5/2. And then we can have plus 1/2. So that's going to give us now, 2's are going to cancel 5.5, which is going to give us u sub 3 is 11/2. And all we'll do is go ahead and generate them. So from this stage, what we've got now is what we've run in week number 1, what we've run in week number 2, what we've run in week number 3, what we've run in week number 4, and what we've done in week number 5. Now, my first question is, how many laps did I do in week 4? Well, the answer is now a total of 23/2, or if you like, 11.5. So I did 11.5 laps in the 4th week. What about how many in total? How many laps in total are in the 5 weeks that I'm doing this? So all we need to do is add this together. So if I add this together, if I add those two together, that gives me 70/2. That's going to give me 86/2. What's 86/2? That's going to be now a total. Let's just write this out. So we've got 1 plus 5 plus 11 plus 23 plus 47. And that's all over now too. So what's that going to give me? That's going to give me 70. Then we've got 86/2, which is 43, plus 1, which looks to be 44. I'll let you do that on a calculator, just in case my mental maths isn't too hot, but that looks okay to me. So we can see now that I've just generated this recurrence relation from an everyday situation. It's highly unlikely that you'd have to write one out, but it just gives you some idea that we're dependent on the last term. So we're taking the last term, multiplying it by 2, and adding a half. And there were lots of different variations. We might square the last one and add a half. We might cube it. We might divide it by 2 and then square it. Loads of different approaches that you can do that will link terms in this particular sequence through a recurrence relation. So that's a brief introduction to sequences. We've looked at recurrence relations, and now in the next video we're going to move on to arithmetic sequences and series. I think the take-home point of this is, whilst it might seem quite tedious initially to write out all of these terms, whatever you do, do keep on top of your work. As we've seen, for example, in this one, that was fairly easy to keep on top of. But if we had now an example like this one here, keeping this good bookwork, as I say, will help you solve the problems.